In this video, we're continuing our discussion of forced vibrations of undamped single degree of freedom systems. So we introduced the response for a simple spring mass system in the last video, and then here we're going to consider the rest of these sections. So first we're going to look at the response at resonance. So all of our results so far are not valid for the special case of a forcing function operating at exactly the natural frequency. So this was the equation of motion for our system. So again, a single degree of freedom undamped system with being forced at with a harmonic forcing function, and here the forcing function has the same frequency as the natural frequency, so sine pt instead of sine omega t. So omega is equal to p. So the homogeneous solution we know is a sine pt plus b cosine pt. And the total response is the sum of the homogeneous solution and the particular solution. So we now need to consider what is the particular solution in this case. So we cannot choose the particular solution of the same form as the forcing function like we did in the previous approach, because we already have this sine pt in our equation, or in our solution here. So we can't just take xpt is equal to c sine pt. So the limitation that xpt is not equal to c sine pt is a special case at resonance only. So our assumed solution now has this form. So x of p is equal to ct sine pt and d plus dt cosine pt. So we have to add this additional t in the solution of this differential equation. So differentiating our particular solution, we can see that xp dot is this expression here, and xp double dot is given as shown here, which we can rearrange and simplify to as the expression here. So now this is our xp double dot, and so if we plug this into the full governing equation, we have m xp double dot plus k xp dot is equal to f naught sine pt. And dividing by m and noting that k over m is equal to p squared, we can see this expression here. So these terms, k over m, go to p squared. So we can replace them as p squared in here, and then we can see that we've got these p squared ct sine pt. These terms can go away, and these two terms can go away. So our governing equation then becomes this expression here. Okay, so this was our expression. We want to find our c and our d, so we can compare the coefficients of the cosine and the sine terms to see that c is equal to 0 and d is equal to minus f naught over 2mp. So this comes from this, and then this comes from comparing these two terms. So substituting c and d into the complete response gives us this. So again, this is the homogeneous response plus the particular solution. And again, a and b can be found from the initial conditions as before. So if, for example, if we have 0 initial conditions, then a and b are given as shown here. So a would be f naught over 2mp squared and b would be equal to 0. But this is only for the case where our initial conditions are 0. And then the total response would become this expression here. So now we can see that there is a t term in front of the cosine. So this indicates that the response will actually increase without limits as t goes to infinity. So if we look at the expression again, we have this t here. So as t increases, this is always increasing. And so it will increase without limit as t goes to infinity. So we get the shape of the response would look something like this. It it would have this oscillatory behavior, but it would continue to grow forever as time goes on. So our previous analysis indicated that the steady state response at resonance has an infinite amplitude. Here we see that the amplitude actually continually grows, so that the steady state solution of an infinite amplitude is actually never reached. Any real structure would break long before this occurred. So a real structure operating at resonance with little damping would just the response would continue to grow until the structure breaks. Okay, so let's look at a particular case of forced vibrations, which is due to a rotating imbalance. So this is a very common cause of forced vibrations in real systems, in machinery. So you have some sort of machinery that is rotating, and if there's an imbalance in the mass, then it can cause what we have is a rotating imbalance, and it can cause these forced vibrations. So let's look at what happens in that case. So, for example, if we have a machine with the total mass, big M, moving vertically, if we have little m is a rotating mass that's included within our M. The machine body, which is without the rotating mass, so m minus little m, vibrates vertically with position x of t. So we can use this coordinate here. The whole body here is vibrating vertically on this spring support with this coordinate x. The eccentric mass then moves relative to the machine body. So this eccentric mass is rotating in this direction. The vertical component relative to the machine body is E sine omega t. So this is the vertical component of the motion of that rotating mass. So that's this here. So the total vertical displacement of the eccentric mass is then x plus E sine omega t. So the free body diagram, mass acceleration diagram of this system is shown here. So we've got the acceleration of the machine body is m minus m x double dot, and the acceleration of the the eccentric mass is m, and then the second derivative of its position, which is x plus E sine omega t. And then the force on the free body diagram is just the force in the spring, kx. So writing Newton's laws, sum of F equals ma, we have minus kx is equal to acceleration of the machine body plus the acceleration of the rotating mass. So we can just rearrange this here. So this is taking the derivative of this, ends up here. The m, little m, x double dot terms go away, and we get big M x double dot plus kx is equal to little m e omega squared sine omega t. Where this looks like the familiar form of the equation of motion of a forced system, where now the force, the F naught is equal to m e omega squared. So this is the same equation of motion that we obtained previously with F naught as m e omega squared. So we know the solution to the steady state response is x is equal to x sine omega t minus phi, where x is our F naught divided by multiplied by the dynamic magnification factor. So F naught over 1 minus omega over p squared, the absolute value of that. And now the F naught over k. So F naught over k is this. And phi is the phase angle is 0 below resonance, and pi when it's above resonance. So we can note that m e omega squared over k we can multiply this top and bottom by m and rearrange this slightly. So this m over k is just 1 over p squared, the natural frequency. So this can be written as me over m times omega over p squared. So we can then write our response as the steady state amplitude as mx over me is equal to omega squared over p divided by 1 minus omega squared, or omega over p squared. So this is the amplitude response for forced vibrations due to a rotating imbalance. And we can plot this response amplitude for the rotating balance, and we get this this behavior here. So at slow speeds, so when omega over p is small, goes to 0, then the me omega squared is small, so the response tends to be small. So this, as omega over p goes to 0, the response actually goes to 0. And at very high speeds, omega over p is much bigger than 1, then mx over me is approximately equal to 1, so m ends up being approximately equal to 1, so mx is approximately equal to me, and the system remains approximately stationary. So as you can see as we get out in this direction. So another important case where we can get where forced vibrations is important is when the base is actually causing the forced vibration. So say we have a system sitting on some sort of base, and the base is able to move. If the excitation is applied to the base, then we can kind of understand what happens in that case. So the difference here compared to the previous case, in the previous case, the force was being applied to the mass itself, and now the force is being applied to the base, so where there's a spring connecting the mass and the base. So this is what happens in response to some external harmonic force again. So let's look at the free body diagram, mass acceleration diagram. So in this case, acceleration is mx double dot, and the force in the spring now is going to be x, which is the displacement of the mass. It's going to be k times x minus a sine omega t, where a sine omega t is the motion of the base. So basically the stretch in the spring is going to be the amount that x goes up minus the amount that y goes up. So applying Newton's laws, sum of F equals ma, we get minus k x times minus a sine omega t is equal to mx double dot, where a here is just the amplitude of the vibrations applied to the base. And it's important that this is amplitude, not acceleration, as the notation is similar. So what we get when we simplify this is mx double dot plus kx is equal to ka sine omega t. So again, this is the same as what we came up with previously, but in this case, our f naught is equal to ka, so this term here. So the equation of motion is the same, so our results of the previous analysis are also applicable. So the particular solution in this case is, so it was f naught over k times the dynamic magnification factor. So f naught over k in this case is just the a. So this is based on our previous work to get to equation 4.6, noting that x of t is equal to xp of t when we're looking at the steady state response. So now the static deflection, f naught over k, as we said, is equal to ka over k, which is just a. So that's why we have that, that term there. So the dynamic magnification factor also takes into account the base moving dynamically. So another important or an interesting phenomenon that can occur is called beating. So this happens when the forcing function is almost the same as the natural frequency. So if we have a system subject to a simple spring mass system with forced vibrations, f naught cosine omega t, this is the total response of our system. And so let's illustrate the concept of beating with the initial conditions of 0 initial conditions. So the constants become these values here. So the total response is given as shown here. So we have this cosine pt and cosine omega t terms. So we end up with something like this, cosine omega t minus cosine pt. Now we can use a trig identity to rewrite this. So cosine A minus cosine B can be written as the product of these two sine terms. So let's do that with our system, or with our response here. So now you see we've got this sine p minus omega t over 2 and sine p plus omega t, p plus omega over 2 times t. So now if omega is close to p, then the value of p minus omega is small, while the value of p plus omega is large. So this results in rapid oscillation with slowly varying amplitude, which is known as beating. So this is what the beating response looks like. We get these, we have these two frequencies in the response. One is p minus omega and one is p plus omega. So this p plus omega is this high frequency component, and then the p minus omega is this slowly varying kind of lower frequency component here. And so just in the notation here, this omega n is p and this omega n is p. So yeah, this type of response is characteristic of this phenomenon called beating. Okay, so the last thing that we want to talk about in this chapter related to forced vibrations is something called transmissibility. So transmissibility is a measure of how much force is transmitted to a support structure during vibrations. So this is a key concern in many vibrating systems because it has the potential to cause damage, to cause noise, and to cause wear. So the transmissibility ratio, or TR, is defined as the maximum force applied to the supporting structure divided by the maximum disturbing force, where the disturbing force is like the forcing function. So how much of that forcing function can cause some amount of force to go to the supporting structure. And so this transmissibility ratio lets us understand the amount of that force applied to the supporting structure. So if we consider our system, our spring mass system, being forced with F naught sine omega t, the maximum disturbing force on the mass is F naught. So this is our disturbing force. And the force applied to the structure, which is this here, is applied through the spring. So the only thing connecting our mass to the structure is this spring. So the force applied to the structure is through the spring. So we need to consider this in the response of the system. So the steady state response of the system is x is equal to x sine omega t, where x is F naught over k over the absolute value of 1 minus meg over p squared, which is our dynamic magnification factor. So now we want to know the maximum force transmitted to the structure. So we said that the force transmitted to the structure was just through the spring, which was equal to, so that's equal to kx, where x was equal to this big X sine omega t. So the maximum force is when x is the maximum, which is when it's equal to, when sine omega t is equal to 1, and the maximum is just equal to this amplitude big X. So the maximum force transmitted to the structure is Ft max is k big X, which is F naught, divided by absolute value of 1 minus omega over p squared. So that means the transmissibility ratio is the ratio of our maximum force transmitted to the structure divided by the maximum disturbing force applied to the mass. So that's F naught over 1 minus omega over p squared divided by the maximum disturbing force, which was F naught. So if we simplify this, we can see the expression here. So this is the disturbing force. We You can cancel those things out and we get that expression. So for a simple spring mass system, the transmissibility is actually the same as the dynamic magnification factor. So this, if you go back and look, is exactly equal to the dynamic magnification factor. Now, if the base is excited rather than the mass, then the maximum disturbing force is now Ka. So if the base, so here we're applying the excitation to the base. So the maximum disturbing force, which is the force applied to the mass, is actually coming through this spring now. So the maximum force in the spring is going to be Ka. And the force transmitted to the supporting structure is K times the kind of difference between x and y. So x of t minus a sine omega t, where x is the steady state response of the mass that we previously found as this expression here. So this means that the force transmitted to the support is given by this expression, which we can simplify as shown here. We've got a sine omega t in both of these terms here. So the maximum of this is the amplitude, which is given as this here. So if you recall on the previous slide, we had f t was this multiplied by our sine omega t. So the maximum that can be is this term, which is this given here. And we can rewrite this to combine these two terms here by multiplying top and bottom by 1 minus omega over p squared. And then factoring out this a, so you see that has come out here. So we can simplify this as we can see here. So ft max is given by this expression. So Ka times omega over p squared divided by absolute value of 1 minus omega over p squared. So now the transmissibility ratio again is the maximum force transmitted to the structure divided by the maximum disturbing force. And we can just plug in the two expressions that we found, or that we showed, to find the transmissibility ratio. So we can cancel out the Ka's, and we see that the transmissibility ratio in this case, which was base excitation, is given as this expression. So omega over p squared over absolute value of 1 minus omega over p squared. So if we plot the transmissibility for undamped base excitation case as a function of omega over p, so we've got our response, the transmissibility here, omega over p squared over 1 minus omega over p squared, as a function of omega over p, we get this shape here. So as omega over p goes to 0, you can see that because of the numerator here, the transmissibility would go to 0. And then as omega over p gets large, these two terms, the one sort of becomes negligible here, and then because of the absolute value, we'd end up getting that this transmissibility goes to 1. And then you can see at resonance, as omega over p is equal to 1, this denominator would go to 0, so our transmissibility would go to infinity.